All right, it's time to start Laplace transforms. So where are we thus far? We've basically sort of got two ways to solve differential equations, if you will. One method is the method of undetermined coefficients, which is a bit cumbersome, let's just say. And then we've also just learned this method of convolution. Okay. And so now we're going to move into Laplace, which is an easier way. But to motivate it, I want you to consider an analogy. And so Laplace is going to be kind of like this. So we know we can change meters into feet. How do we do that? If you know how many meters you have, you multiply by this transfer function, which is just a number, and you get the number of feet. Or you can go the other way. All right. It would be really nice if we could have something to do something similar with systems. What do I mean by that? Suppose you could get the input, multiply by the system, say have the initial conditions, sort of multiply by the system, and get the output. That would be nice. With Laplace, we can sort of do something like that. All right. So with Laplace transforms, what happens? There's sort of a three-step process. Step one, we find the Laplace transform of the input, the system, and the ICs. We kind of multiply them all together, and then you would find the inverse Laplace transform to take them back into time and get your answer you got before. All right. So let's start taking a look at that. Laplace transforms go between two different domains. And so we have the time domain, t, and then S, which this is usually called the frequency domain, but it's also S is any complex number. So when we go to do this with Laplace going from t to S, t is any real number representing time. S is any complex number representing a point on the complex plane. All right. What is the Laplace transform? Well, this is the definition of it. You should have seen this. This is typically given in a differential equations course. So you hopefully have seen some of this. The Laplace transform of f of t is said to be f of s. So the use of s in Laplace transforms pretty much universal of doing that. So we're going from f of t to f of s. And then there's an inverse Laplace transform. We can go f of s back to f of t. The process of doing this is this integral. 0 to infinity f of t, e to the minus st, where s is just some constant complex number, and you just don't care what it is, sort of, dt. All right. Now, keep in mind, we got to get a Laplace transform of our system. All right. And if we're having a differential equation and we're trying to solve one, so we can have a differential equation of the input, or we can have a Laplace transform of the input or the output, whatever. But when you have a differential equation, let's say you have y dot plus 6 y of t equals x of t. So I need to be able to Laplace transform the y, and we'll just say, so y of t goes to y of s. But how do you Laplace transform y dot of t? Okay. And so that's what we're going to look at really quickly now. And so we're actually going to derive it. And so Laplace transform of f dot of t, well, all you have to do is stick f dot of t into this, and whatever that integral is, would be that. All right. But you can evaluate this based on integration by parts. So we're going to let u of t equal this e to the minus st, so you can form du. And we'll let dv be f dot dt. So when you integrate that, you get v equals f. So for our differentiation by parts always has a u and a d. If you substitute all this stuff in, so this is from e to the minus st f of t from this work. All right. And here we have now s times this integral, which is the same one we had here. So it works out that this is minus f of 0 because we always presume that t, as t goes to infinity, it dominates the s. And so this term, e to the minus infinity times some s, goes to 0. And then here we have sf of s. I'll leave you to check this on your own time. And you hopefully have seen this in the math class already. Here we have Laplace transform of f dot of t, that equals s f of s minus f of 0. That's just reordering this. Now, once we've accomplished this, we can do differential equations. If you have y, you have y dot, maybe you have y double dot. All right, let's apply that. So Laplace transform of f dot of t, if you put an f dot in here, that would say you would get s f dot of s minus f dot of 0. But f dot of s equals this piece, so we can substitute that in. Okay, so we would have s squared f of s minus s f of 0 minus this f dot. If we take this to arbitrary n number of derivatives, so this is the nth derivative of f of t, you'd have s to the n, f of s minus, now when we just proceed to go down order by order in s until you get s to the 0th power, which would be 1. S to the n minus 1, f of 0, minus s n minus 2, f dot of 0, so on and so forth. That's how we do this. Okay? So, given these properties, we can now look at finding the Laplace transform of a differential equation. We'll do that next.